Welcome to The Explainer. We hear it all the time. Things are connected. More ads mean more sales, right? A better diet leads to better health. But how do we really know? How do we separate what's a real, genuine connection from what's just a random coincidence? Well, today we're going to pull back the curtain on the tool that helps us do exactly that. It's called simple linear regression.
So let's start with a puzzle, one our brains are trying to solve literally all the time. You see two things moving together, you spot a pattern, and you think, aha, they're connected. But what does that connection actually mean? Is one causing the other? Okay, sometimes the link feels super obvious, right? It just makes sense. Take height and weight. As someone gets taller, yeah, their weight generally goes up too. It feels like a direct physical cause and effect thing. And other times, we just assume there's a cause because, well, it makes sense from a business perspective. A company pumps more money into ads, and what do we expect? Sales go up. It seems like a no-brainer. One directly pushes the other. But then, you get these other situations, things that are connected just by sheer random coincidence. I mean, think about it. Does knowing more about statistics somehow cause you to own more cars? Almost certainly not, right? There's probably zero real connection there. And this gets us to a golden rule in data, something you absolutely have to remember. Just because two things move in sync, it doesn't mean one is making the other happen. And that's our big challenge today. How do you tell the difference? How do you spot a real relationship versus just a random fluke? This whole idea of mixing up correlation and causation, it's such a common mistake, we can actually give it a name, the correlation trap. But don't worry, because today we're going to learn how to avoid it and how to get out if you're already in. All right, so the tool that's going to be our guide through this maze, the simple linear regression. Basically, it lets us build a mathematical model of a relationship. We've got two key players here. The dependent variable, that's the thing we're trying to explain, like sales, and the independent or explanatory variable, which is the thing we think is doing the explaining, like ad spending. So you can really think of it like a special kind of magnifying glass for data. It lets us look at a big, messy cloud of data points and filter out all the random noise. And what's left? The real, predictable pattern, the signal that was hiding in there all along. Okay, so how does this thing actually work? How does it look at all that data and pull out that one clean pattern? The core mission here is actually pretty simple. The goal is to draw one single, straight line that slices right through all those data points and does the best possible job of summarizing the relationship between them. And the way it does this is with a really clever method called ordinary least squares, or just OLS for short. Okay, here's the basic idea. Imagine you just start drawing random lines through your data. For every single data point, you can measure how far away it is from the line you drew. That distance, straight up or down, is the error. It's how wrong your line is for that specific point. Now here's the cool part. OLS squares each of those errors. Why? Well, that does two really smart things. First, it gets rid of any negative numbers. And second, it really punishes the big errors. Then it just adds up all those squared errors. So what's the best fit line? It's the one and only line that makes that grand total of squared errors as tiny as it can possibly be. It's mathematically perfect. Okay, great. So we found our best fit line, but is it any good? I mean, how do we know if it's a great fit, a decent fit, or a terrible one? How well does it really describe what's going on in our data? For that, we've got a really handy little report card. It's called R-squared. Think of it as a score from 0 to 100%. And it tells us exactly what proportion of the change in our Y variable, our outcome, can be explained by the change in our X variable. Let me give you a real-world example. In a study looking at gasoline prices, the R-squared between the price of crude oil and the price you pay at the pump was 94.3%. Wow, that is a really high score. So what does that 94.3% actually mean? It means that a huge chunk, almost all really, of the ups and downs in gas prices can be explained by the ups and downs in crude oil prices. That leaves this tiny little slice, just over 5%, that has to be explained by, well, everything else. Things like local taxes, or maybe issues with the supply chain. But hold on, even with a stellar grade like that, we can't stop there. We have to put on our skeptic's hat and ask one more super important question. And that question is this relationship we found real, or did we just get lucky? Could it be that this strong connection is just a random fluke that happened to show up in our particular set of data and it wouldn't show up again if we collected more? To figure that out, we look at the standard regression output. It kind of looks like this table here. It's got a lot of numbers, but we're going to zero in on the row for our predictor variable, in this case, crude, and we're going to look all the way to the right to that last column labeled P. That's the p-value. And look at that. For crude oil, it's basically 0. Now, there's a really simple rule of thumb for this. If that p-value is really small and the usual cutoff is less than 0.05, it means that the chances of seeing a relationship this strong, just by pure luck, are incredibly low. So it gives us confidence that our finding is real, that it's statistically significant. Here's a little rhyme to remember. If the p-value is low, the relationship is a go.
All right, so let's recap. We've found a strong relationship and we've confirmed it's statistically significant. That's awesome. But now comes the important part. How do we use this newfound power to look into the future responsibly? To use regression wisely, you've got to keep 3 big rules in mind. First, and we've got to keep saying it, correlation is not causation. Even a perfect model doesn't prove one thing causes another. Second, be really careful not to extrapolate. Just because a relationship holds true for the data you have doesn't mean it'll hold true for values way, way outside that range. And finally, remember that every model has some basic assumptions. A good analyst always checks to make sure those assumptions aren't being broken. And that really gets to the heart of it. Look, regression is an incredibly powerful tool for understanding the world and making forecasts. But with that power comes a huge responsibility to understand its limits. Because at the end of the day, the tool is only as good as the person using it. So here's my challenge to you. As you go about your day, start looking for these patterns. They're everywhere, in the news you read, in your job, even in your hobbies. Now that you know how to spot a potential relationship and how to test it, what hidden story will you look for first?